Alright, so in this section 7-6 we are continuing learning on how to solve different trigonometric equations. So last time we looked at solving certain trigonometric equations, and this time we're going to look at a few different types of equations to solve. Once again, I've given you the same chart because you got to make sure you take these things into consideration: the period, the domain, and the range of each one of the trig functions as you're going through and solving. So that's the case again, so I've given it to you again at the beginning of the notes here. So let's try a type like this. So we've got 2 times sine squared x plus 3 cosine x minus 3 equals 0. Alright, so we're dealing with sine squared this time. Alright, now, here's the first thing that you want to try to accomplish in one like this. You see how you've got 2 different types of trig functions? In order to be able to solve it, you want to try to get that converted to the same trig function. I either need both of these to be sines or both of these to be cosines somehow so that we can combine them. Alright, now, when we look at this, okay, if I'm just dealing with cosine and say, well, how do I turn cosine into sine? Well, there's really no way to turn cosine into a sine with any of the identities. But there is a way to turn sine squared into cosine squared, and at least then I would have both of them as cosines. So that's what we're going to do. We're going to use this Pythagorean identity. And so what we'll do is we'll change sine squared x into 1 minus cosine squared x using that identity. So when I do that, here's what it becomes. 2 open. So I'm changing sine squared to 1 minus cosine squared. Okay. And then the rest of that will be the same, plus 3 cosine x minus 3 equals to 0. Okay. Alright, so from here, what's next? We can use the distributive property. That'll make 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals to 0. Alright, so from here we can go 2 minus 3, combine that and get negative 1. So let's go ahead and do that. So now we got negative 2 cosine squared x plus 3 cosine x, combine those together, minus 1 equals to 0. Okay, so at this point now we have it in a form that we could actually go through and factor into a product of 2 binomials. But actually, before we do that, why don't we go through and multiply everything by negative 1 so that this leading coefficient is positive. So let's make it 2 cosine squared x minus 3 cosine x plus 1 equals to 0. So I just went through and multiplied everything by negative 1 so that this leading coefficient is positive, which makes it better for me when I go to try and factor. Alright, which we'll go ahead and do now. So I want to factor this into a product of 2 binomials. And when I do, remember the first 2 multiplied together have to give me 2 cosine squared x. So what do I need here? I need a 2 times the cosine of x, and I need a cosine of x. Okay? And so the next thing I need to focus on is how can I multiply these 2 together to get a positive 1, but get a negative term in the middle, right? So that would have to be a negative times a negative make a positive, because that's the only way that my ending term can be positive and my middle term would be a negative. And then, of course, the only way to get 1 is negative 1 times negative 1. Let's double check the middle term and make sure we're good. Negative cosine x minus 2 cosine x is negative 3 cosine x, so we have factored it correctly. And, of course, once you factor, now we have it into a form where we can split it up into 2 equations. Zero product rule, either 2 cosine x minus 1 equals 0, or cosine x minus 1 equals 0. Okay? And so to go and solve this one now, I'll move this over to the other side, make it positive, and divide by 2. So I would have cosine of x equals to 1/2. And on this side, we'll move the 1 over, and we have the cosine of x equals to 1. Okay? So each one of these should yield me solutions. And so let's see if we can figure out what those solutions are. So remember on this first one, okay, so I'm looking for an angle whose cosine is 1/2. And remember the cosines is going to be the x value of the coordinate, right, when I go through and take a look at it. And so I'm really looking on the unit circle to find period pi over 2, by the way, so take that into consideration. Oh, I forgot also to make sure that this value is within the range, so that's something we also need to check. So the range for cosine is from -1 to 1. 1/2 is within that range, and 1 is also within that range because it is equal to 1. So we're good on both of these. Both of these will yield valid solutions. So now, again, I'm looking on the unit circle for an angle whose cosine is 1/2. An angle whose cosine is 1/2. Remember, the cosine is the x-coordinate. So let's go around and look for 1/2 on the x-coordinate. There's 1 at pi over 3, so that'll be 1. Pi over 3 will be a solution. See if there's any more here. And we're going all the way to 2 pi, so I'm looking for 1/2. That's a -1/2. -1/2. There's a 1/2. And then that's at 5 pi over 3. 5 pi over 3. Now let's see what solution we can get from this. Cosine is equal to 1. Cosine is equal to 1. And so I need 1 in the x column, or the x coordinate. There's 1 here at 0. Is there any other one where there's a 1 there? -1 doesn't work. 0 doesn't work. So 0 is the only solution from that equation. All right? So those are my 3 solutions over the interval of the first period, which is from 0 to 2 pi. Of course, not including 2 pi because that would be the first repeating value. It would be the same as 0. All right? Okay, so now we need to take these now and write it as a general solution because, like I say, they could ask you for solution over a certain interval, and it can be any interval, right? We talked about that last time. Or they could ask you what is the general solution, or what is all the solutions. All right, so to take that and put that in the form for the general solution, we'll take it pi over 3. We will take each interval solution and add, right, multiples of the period, which the period's 2 pi, so that'll be 2 in pi for that one. 5 pi over 3 plus 2 in pi. And for the last one, that would be 0 plus 2 in pi, which I could probably just write as 2 in pi. But if you wanted to keep the form right and make sure that you emphasize the fact that 0 is the interval solution, you could write it as 0 plus 2 in pi. That's fine as well. Okay, either one will work. Let me see. What else we got here? That's it. That's the general solution. All right, so there you go. Next one. Okay, so in the next one, we're trying to find all of these solutions for cosine of x plus 1 equals to the sine of x. Okay, and we're on the interval for the period, which is from 0 to 2 pi. All right, so now on this one, we want to start off with the same strategy. We want to try to either get both of these to be cosines, or we want to try to get both of these to be sines. Now, last time we already had one that was squared that we could convert and get it to match cosine. However, that's not the case on this one. And remember, with our identities, there's no way to turn just a sine into a cosine or a cosine into a sine. There's no way of doing that, right? Because with our identities that we have, reciprocal and quotient identities, there's no way to just turn a sine into a cosine or a cosine into a sine. And you've got some down here that would do it, but that would actually more complicate the equations, right, if you did it that way. So you might want to be careful with these co-function identities, because that would further complicate things instead of making it simpler. However, here is one thing that we can do. We can actually square both sides and then convert like we did here. Okay? Because remember, once we get it up to squared, then we can have something to work with. So really, our strategy here is the first thing that we want to do is actually square both sides of this equation. So I'm going to go. Let's see. I'm going to go cosine x plus 1 squared equals to sine squared x. Okay, so we're going to square both sides. That is the first strategy. I can square this out now. So cosine squared times cosine squared, or excuse me, cosine times cosine is cosine squared x. Then I would have cosine x plus cosine x, which is 2 cosine x. Then I would have 1 times 1, which is 1, so that's a plus 1. And then that's still going to be equal to sine squared on the other side. All right. Okay, so from here now, let's take a look at what we've got. Okay, we've got a cosine squared and a cosine, and then we've got a sine squared. So what would be easier, to convert the cosines to sines or to convert this sine to a cosine? It'd be easier to convert this to a cosine because it's already squared and we have an identity that would convert it. But if we attempted to convert these to sines, I would still have this to deal with. All right. So let's convert this sine squared into something with cosine squared. So when we do that, we'll have this. It'll be cosine squared x plus 2 cosine x plus 1 equals sine squared. Let's see what we can change that into. We can change that into 1 minus cosine squared, which is what we're going to do. So sine squared becomes 1 minus cosine squared. And so now we have got all of these into cosine, which is getting closer to what we're trying to accomplish. All right, so what can we do here now? Okay, if we get all these terms set over to one side, that would help us some. So I'm going to move this cosine over and change it to plus. Well, when I got cosine squared plus cosine squared, that's going to make 2 cosine squared x. The plus 2 cosine is already still here. Nothing's changing with that. That'll come over and be 1 minus 1, which is now gone. So here's where we're at when we move those terms over. All right, so from here, probably the best thing to do would be to factor out a 2 cosine out of this. So when I factor out a 2 cosine x, what's it leave me with? In the first one, we're just left with cosine x plus, and 2 cosine x divided by 2 cosine x is just 1. All right, so we pulled that out of there. Zero product rule will give me either 2 cosine x equals to 0 or cosine x plus 1 equals to 0. Let's see what solutions we get from here. Divide both sides by 2, and I've got cosine x equals to 0. And so from here, now I'll move this over, and I've got cosine x is equal to negative 1. All right, now remember, once you get down to this point, before you go any further, make sure that this is in the range for the trig function. Cosine are 0 and negative 1 in the range. 0 is in the range, negative 1 is in the range because it's equal to, so we're good there. So both of these will yield solutions. Let's see what those solutions are. It's going to be x equals, so for this first one, I'm looking for angles whose cosine is equal to 0. Remember, cosine is the x value. I'm looking for x values of 0. X values of 0. And the period's all the way around. So x value of 0, there's 1, that's pi over 2. So we'll write that in. pi over 2. Okay, so good shape there. Let me see here. Pi over 2. Got that one. Any more zeros for an x coordinate? See one right here, which is 3 pi over 2. We'll write that one in. 3 pi over 2. Write that one in. And then see if there's any more. No more zeros. So now I want cosine of x to be equal to -1. So I need an angle whose cosine is -1. So now I'm looking for -1s on the x coordinates. Let's see if we can find one. There's one at pi. And I believe that's the only one. Yes, it is. So we'll put in pi there. Okay. All right. Okay, so here are the solutions that we get. Now, here's something else to take into consideration before we finish this up. Okay, and I don't know if you guys remember early last semester when we were solving equations. One thing that we had mentioned is the fact that if you square both sides of the equation, you introduce the possibility of what is known as extraneous solutions. All right, extraneous solutions. All right, so we are going to have to double check each one of these solutions to see if they're extraneous or not. Okay, because remember, anytime you square both sides of an equation, you introduce the possibility of getting some extraneous solutions. So how do we check these solutions? Well, you would check them the same way you would normally check the solutions on any equation. Let's plug them back into the original equation, and then we'll see what we come up with. So we'll check pi over 2 first. So we need to check cosine of pi over 2 plus 1 and see if that's equal to the sine of pi over 2. Alright, so that's the first thing we'll check. Alright, so the cosine of pi over 2 is 0. 0 plus 1 equals to the sine of pi over 2, which is 1. And so 0 plus 1 equals 1, so that's a valid solution. We'll keep that one. So the next one we want to check, 3 pi over 2. So we'll go the cosine of 3 pi over 2 plus 1 equals to the sine of 3 pi over 2. Okay, 3 pi over 2. The cosine of 3 pi over 2 is 0. 0 plus 1. We want to see if that equals to the sine of 3 pi over 2, which is -1. And so, as you can see, 0 plus 1 does not equal -1. And so, actually, 3 pi over 2 is an extraneous solution. Throw it out. Okay, that one will not yield a correct answer to the original equation. What about the last one? Let's see. Cosine of pi plus 1, is that equal to the sine of pi? Let's have a look. Alright, so at pi, the cosine is -1. -1 plus 1 equals to the sine of pi, which is 0. And that is true, so we will keep that solution. So 3 pi over 2 is the only one we had to throw out. But remember, anytime you square both sides of an equation, you must check to see if any of your solutions are extraneous or solutions that don't satisfy the original equation. In this case, we do have one that we had to throw out. So make sure you double check that or you'll get the wrong answer in the end. Now I can take these and say that x equals pi over 2 and pi. Those are my interval solutions for 0 to 2 pi. And I can say that x equals pi over 2 plus we got cosine, so the period is 2 pi, so it'd be 2 in pi, and pi plus 2 in pi. Those will end up being my general solutions. Alright, so there you go. So like I say, anytime you square both sides, you do have the possibility of introducing extraneous solutions. Make sure you check that in the original equation anytime you have an equation that you have to square both sides. Like in this case where you've got a cosine and a sine, the only way that you can turn them both into the same function is to square both sides and use that Pythagorean identity. And once you do that, though, you've got to check for extraneous solutions. So keep that in mind on any one where you have to utilize that technique. All right, what's the next thing that we come to? Okay, so the next type of equation we come to is one where we don't just have an x or a t here inside the cosine function. This is 2 cosine times, or 2 cosine of 3t minus 1 is equal to 0. So this is noted as a multiple angle function. All right, functions of multiple angle. Let's see how we handle that. All right, so the first thing I'll do here is I'll go 2 cosine 3t equals to 1. So I'm moving that 1 over to the other side. We can divide by 2. So the cosine of 3t equals to 1/2. All right. So now at this point, okay, I'm ready to check for domain. So the cosine of the angle is 1/2. And so we'll want to see if 1/2 is in the range for cosine at this point. Cosine range -1 to 1. We're in good shape. Okay, so now here's the deal though. I'm looking for an angle whose cosine is 1/2, but remember, this is not, this wouldn't be t equals these angles. This would be 3t equals these angles. So that's the first thing that we need to make sure that we are aware of. So 3t would be equal. So now I need angles whose cosine is 1/2. Cosine, again, is the x value. So let's go through and see if we can find x values of 1/2. Here's one at pi over 3. Pi over 3. All right. And here is another one at, let's see, 1/2. There's one at 5 pi over 3. One at 5 pi over 3. Pi over 3. All right. Now, remember, these aren't solutions yet to my equation because I don't want to know what 3t equals. I want to know what t is going to be equal to. So I've got to take each one of these now and divide them by 3. So that means that t is actually going to be equal to pi over 9 and 5 pi over 9. So I got to divide both of those by 3. So that's what my t is going to be equal to, and that's going to be the interval solution. All right, that's your interval solution, right, from 0 to 2 pi. All right, so there's your interval solution, right? And so now from here, we need to take this and write this as a general solution, right? As a general solution. And so what we'll have to do now is, just like how we adjusted the angle, right? Just like how we just had to adjust the angle, you've also got to adjust the multiples of the period that you're adding to get the general solution. So, like for example, I can say this is pi over 9, right? I can say this is pi over 9. But instead of just adding 2 pi in, just like how we divided the angle itself by 3, you also have to divide the period by 3. So that's going to be plus 2 in pi over 3. So like I say, just like we adjusted the angle by dividing it by 3, to keep it equal, we also have to adjust the period in the general solution that we're adding to it by 3. Because remember, before you plug into the function, you're going to take whatever's here and multiply it times 3. And so what that means is, in order to keep the cycle, the periodic cycle going correctly, we also have to adjust the period that we're adding to, multiples of the period, by 3. You see what I'm saying? To make it still land in the right place after it's multiplying by 3. That's the adjustment that needs to be made to keep it on track, in other words. Likewise, we'll do it for the other solution, which is going to be 5 pi over 9 plus 2 n pi over 3, and then that's going to be your general solution. Alright, so like I say, with these multiple angles, once you get to here, whatever adjustments you have to make to solve for the t, you got to make sure you make that same adjustment to the general solution, to the period, to keep it equal. Alright, so that's what we're looking at there. Okay? Alright, so we have another multiple angle equation that we're going to be looking at. And so let's see what we can do here on one like this. I've got 3 times the tangent of x over 2 plus 3 equals 0. Let's move the 3. 3 tangent x over 2 equals to negative 3. Alright, so there's my first step. From here now we can divide both sides by 3. Tangent of x over 2 is equal to negative 1. Alright. Okay, at this point we need to check for range. Tangent, what's the range? All real numbers, so we're good. Let's see. So from here now, I'm looking for the angle, right, whose tangent is equal to negative 1. I'm looking for angles whose tangent is negative 1, but remember, that's not what x is equal. That's what x over 2 is going to be equal to. And so let's go through and see if we can find it. Remember, tangent is y over x, so I'm looking for the y over the x to be equal to negative 1. The y over the x to be equal to negative 1. Let's see where we can find that. Let's see, y over the x to be equal to negative 1. So they're the same here, but it wouldn't be negative 1, right? They're the same here, and it would be negative 1. So 3 pi over 4, there's a candidate. 3 pi over 4. And remember, with tangent, period is from, the period is pi. And so really I can stop here. I don't need to check the other half of the circle because I'd be repeating period, and then those solutions would be picked up in my general solution. Right? So that's really the only one that we need over that interval. Now remember, this is what x over 2 is equal to. So if I wanted to finish solving that for x, I would have to multiply both sides times 2. Right? And when I do, I'm going to get x is equal to 3 pi over 2. 3 pi over 2. So multiply both sides by 2, and then there is your answer for x, and that's over the interval. Alright, that's the interval solution from 0 to pi. And remember, that interval doesn't need an adjustment because this is the x that you're going to plug in here and divide by 2 to get the angle whose tangent is negative 1. So the angle is still correct on as far as the interval is concerned. Now when we take it to a general solution, though, we're going to get x equals 3 pi over 2 plus. Now remember, typically for tangent the period is pi, but I need to take that pi, right, and what did I do here? I multiplied by 2 to get this, multiplied by 2 to get this. So now I'm going to have to multiply the period by 2, and then so that's going to become 2 pi n, or 2 n pi, I should say. So don't forget to make the adjustment. Whatever you do to here to get the x, whatever you do to the angle to get the x, do the same thing to the period to make the adjustment. Okay, that's your general solution. All right. So there we go. Good shape there. What about the last one now? Let's take a look. Okay, so on this one I'm trying to solve secant squared x minus 2 times the tangent of x is equal to 4. So on this one, again, our strategy is we want to try to make both of these secants or both of these tangents if we can. Whenever you've got a squared, that's a good opportunity to take a look at possibly switching the function. And we can do it because what's secant squared equal to? It's equal to 1 plus tangent. So we'll go ahead and make that swap. So that'll be 1 plus the tangent squared of x minus 2 tangent of x. Go ahead and bring the 4 over, make it minus 4 equals 0 because that's the next thing that we'll need to do anyway. And we can combine those together, the 1 minus 4. So we'll have tangent squared of x minus 2 tangent of x minus 3 when I combine them is equal to 0. So we're getting closer. Next thing, we're ready to factor into a product of two binomials. So how do I get tangent squared? That'd be tangent x times the tangent of x. Alright, so two numbers multiplied together to get a negative. So that would be a positive times a negative. I need my bigger number there to be negative, right? And so what that means is, how do I get 3? It would be 1 times 3, and I would need the 3 part of it to be negative to make sure I get negative 2 in the middle. Double check it. That's tangent minus 3 tangents, which is negative 2 tangents. So we're good there. Alright, so now we're down to the point where we have two equations. Tangent of x plus 1 equals 0. Tangent of x minus 3 equals 0. So that becomes now tangent of x is equal to negative 1, and this becomes tangent of x is equal to negative 3. Quick range check reminds you that all reals is the range for tangent, so we're in good shape for whatever's over here. And so to finish that now, let's see what we've got. Okay, so here I've got x equals, so I need angles whose tangent is negative 1. Angles whose tangent is negative 1. I feel like we just kind of ran into that a few minutes ago, didn't we? Angles whose tangent is negative 1, that's positive 1, that's negative 1. So it is at 3 pi over 4. So 3 pi over 4. Okay. So now I'm looking for angles whose tangent is negative 3. Angles whose tangent is negative 3. Now, here's the problem on this one. If you went looking through the unit circle to do y divided by x, you're not going to find any one of these points that yields you a 3. Or did I write that wrong? That's not negative 3, by the way. That should be a 3. I'm going to go ahead and correct that. When it moves over, it'll change that to a 3. Okay, so we're good there. All right. Now, you won't find anywhere on the unit circle that'll give you that value. And here's why. Because the angle whose tangent gives you a 3 is not one of these points that's on the unit circle. So what are we going to do in this case? That's why we're going to be using inverse functions. So what I'll have to do is I'll have to do the inverse tangent to both sides to come up with the correct value of x here. And so if I go ahead and take out my calculator here, we can go to Desmos and we can figure this out pretty quickly. We need the inverse tangent of 3 is what we need. See y'all later. We're still in radians, so we'll go inverse tangent of 3. Huh? Yeah, just leave it on the desk. I'll come get it. Or actually, take it and put it on that closer desk for me, if you don't mind. Okay, so my solution there now, when I do the inverse tangent of 3, would be 1.249, we'll call it. Okay, 1.249. All right. So again, anytime you've got a value that doesn't actually hit any of the points that are listed on the unit circle, you'll have to use the inverse function to come up with the value. Now remember, this is still in radians, so that's why we've got this down here on the unit circle in case we don't have something in terms of pi. 1.249 radians is somewhere a little less than 90 degrees. All right, somewhere a little less than 90 degrees is what this angle would be, and it's just not one that hits on the unit circle. It's not 60 or 90, it's somewhere in between there. And so that's why we had to use our inverse function to come up with it. And so when we're writing it out as our solutions, we could do it like this. We can go x equals 3 pi over 4, okay, and 1.249. That's my interval from 0 to pi for tangent. Okay. And general, we'll go 3 pi over 4 plus n pi, as well as 1.249 plus n pi. That's the general solution. Okay. Now, if we wanted to double check to make sure that we were correct here on this, we could take this 1.249 and plug it in here and see if it gives us 4. As a matter of fact, that would probably be worth doing. So let's go in here and see if indeed secant, let's see, secant squared of 1.249045772 4, might as well go all the way to be exact, minus 2 times the tangent of 1.249045772 4, and you can see that it is 4, so it does check out, so that is a valid solution. All right, so like I say, when you get down to an equation that doesn't land on the unit circle, then you're going to have to use the inverse function to come up with it, and it still is going to be a valid solution. So our solutions here, one of them is in terms of pi, and one of them's not, but they're both radians, so keep that in mind. All right, that's it.